In this last of the 3 lectures, I would like to say something about confinement and some of the things we've learned from the lattice. There's a lot of things that I miss out because people have worked on this for a few decades and there's a lot of material one could cover. So, well, let me start anyway. So let me start with a comment upon an old comment, if you like, on the Wilson loop area law for confinement. We saw in my earlier lectures that you can derive this area law criterion for linear confinement by considering a correlation function, which is down here of very massive fundamental fields here, 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 here. And this, when you integrate them out, this gives these propagators if their mass goes to infinity. And at the same time, it gives the lightest energy between those fundamental fields, which is the potential. So, and if the potential increases linearly with R, then you get, so you have an exponential of the potential times time, this being the energy of the lightest state going this way, apart from the masses of these particles, which has been thrown out. And then, which doesn't depend on R, because it doesn't depend on R. And then if you take the potential to be linear in R, then you get an area here, because you get this and this. So you have the area law from confinement. And one of the things about this is there's a very, if you look at this, it's really a phase here that you've got, and you're averaging a phase, and what you're saying is that it's extremely small. And in fact, there's an old paper going back to the late 70s by Seiler, who, with some technical assumptions, showed that the area law is the fastest possible decay of a Wilson loop. So in some sense, we are getting the smallest possible values for such a phase, which means that, you know, the phase is something with an exponential which of some kind of angle, okay, matrix valued angle. But anyway, it's so it's saying really that there are a lot of fluctuations which are averaging out. Basically, there's a maximum amount of disorder in order to get an area law. So basically, you're looking for a lot of disorder in this kind of phase, to disorder this phase in order to get an area law. So one is looking for mechanisms which might give maximal fluctuations of the fields. And that's, of course, what easily happens in strong coupling, and one can easily show linear confinement there, but that's not where we want to show it. So this is a kind of general remark that really what we're looking for is a lot of fluctuations in order to get that area law, about as much as you can possibly have. Now, let me move on a bit and make some comments on monopoles. And what I'll do is just try to give some very simple picture. So I'm thinking of what do monopoles do to the Wilson loop? Well, we know that, or a magnetic monopole, we already know that from the work of Polyakov, who did this properly. So I'm not going to do it. I mean, what he did was to take a Georgia-Glashow model essentially and have the SO3 symmetry spontaneously broken, so that long distances you have U1 fields, while at short distances you have the full SO3 fluctuations. And you also have two Polyakov monopoles, and those are the monopoles that he considered, and he did the calculations with them and showed that give linear confinement. And that, of course, was very nice because it doesn't have any regularization problems. Here, I just initially will just pretend we're sort of use a kind of continuum language, but of course, you might ask, how do I manage to get monopoles and electric charges at the same time? Well, the way to do it would be, for example, the way Polyakov does it, but let's get into those details. So suppose you have a monopole which is close to the Wilson loop, very large Wilson loop. It's quite close, a distance h from it. Then half of its magnetic flux will go through the Wilson loop. And the magnetic flux is quantized. In my case, I've made the electric charge to be 1, so that the total magnetic flux is 2 pi coming out of the monopole. So pi flux goes through the Wilson loop. And then and in the U1 theory, which is where we are now, in 2+1 dimensions, so that I can draw diagrams. I'll mention 3+1 dimensions later. if you have a flux of pi going through the Wilson loop, it will give you the integral, of course, of the gauge potential around the perimeter is just the exponential of the flux through the through this area, which is pi, so we get -1. So a monopole close to the Wilson loop gives you a factor of -1 in the value of the Wilson loop. They disorder the Wilson loop. Now, suppose we have these monopoles, the gas of these monopoles. One thing we know about a gas like that is that it forms it gets screened, so sort of plasma screening of charges. So we have monopoles and antimonopoles, and they maximize their entropy by being completely random. On the other hand, if they're completely random, then the energies get very large at various points from all the random charges around. And so the screening reduces the fields in such a way that the energy is less. However, of course, you lose a bit in the entropy because it's not quite so random. However, there's a balance in between these effects, and you end up with some kind of, with a screening length, which you can calculate on that basis. So this system is a screened plasma, and will have, as you would normally have in 3 dimensions, and it's got a certain screening length. So I'm going to take the approximation for this brief argument to say that all the monopoles that are beyond the screening length don't contribute at all. Their magnetic flux is completely screened, while the ones within the screening length of the Wilson loop, all their flux goes through the Wilson loop. There's no screening at all. That's obviously an approximation. One could do better if one wished to. But this kind of argument doesn't really deserve such a detailed calculation. So, so what we have is we have monopoles which are within a slab of the Wilson loop, where the thickness of the slab is the screening length on both sides, and their flux within that slab, they will typically be, one will take them to be random. And if they're random, you can actually do a little calculation. Yeah.
Maybe it's a naive question. So this monopole is localized in space and time.
Yeah, so it's really an instanton. So this is, yeah, I should have said that, but we've discussed this model a bit before, so I didn't. This is where in 2 + 1 dimensions, the monopoles are like instantons, they're in space and time. However, the fields from them are exactly the same as a monopole in 3 dimensions. So I will keep calling them monopoles, although I should really call them, people are more often call them monopole instantons, but they are instantons. So this is Euclidean space-time in which they're spreading their fields. But I'm using a language as if there were 3 space dimensions, monopoles in 3 space dimensions, because the fields are the same. And we have an intuition for that. So, but that's a good point to make, actually. So I should have said that. Okay, so let's see. Some slight problem with this. Oh, okay. So consider a gas monopoles. And let's suppose we have little n up there per unit volume. They form a screened plasma with length Ls. And so they lie within this slab around the Wilson loop. That's the volume within which they lie. The ones that affect the Wilson loop are within a slab. Within that slab, I assume that they're random. So if I calculate the Wilson loop with that little model there, what you get is if they're random, I use a Poisson distribution. I don't differentiate between monopoles and antimonopoles because whether you produce a flux of pi or minus pi, it has the same effect. E to the I times pi, or e to the minus I pi is -1. So you get every time you have a number n of monopoles, you get -1 to the n. And this, of course, is normalized. So if I didn't have this factor, then it would be just this. And in this Poisson distribution, mu, of course, is the average number of monopoles, which is in order for this to sum up over n to be 1. And that is the number per unit volume times the screening length times the area of the Wilson loop. That's the whole volume of the slab. And I put in a 4 there because you have a slab both above and below, and monopoles and anti-monopoles, so another factor of 2. So now with this -1, when you sum this up, you don't get 1 as you would without this, you get e to the -2 mu, which is precisely exponential of minus the area. And that's because this is really, I mean, what's happening here is that if you have an odd number of monopoles plus anti-monopoles, the Wilson loop flips sign, and if it's an even number, it's +1. And the net result is the probability of is the difference between the probability of even and odd. And that's an extremely small number, which is exponential of the area. That's what comes out. So you can get in this way, you can see just by the randomness of the fluctuations, and if the fluctuations are sufficiently random, they will actually be proportional to the area of the Wilson loop, the fluctuations, and that naturally gives you an area law. So that's just a hint. I mean, I'm not saying take this model seriously. I just wanted to show how you can very easily get an area law from that kind of fluctuations which are random, and therefore they provide something which nearly will give you something like an area law. Yeah. But then the problem is, of course, to find such fluctuations. What are they? In this case, in this model, we just set it up so it's the monopoles doing it, but that's a solvable model anyway, so haven't achieved a great deal. So you need uncorrelated fluctuations with opposite signs with a number that is proportional to the area of the loop. So I used a kind of continual language there. Okay, so that was a simple argument. Let's move on to, we are on the lattice. In the U1 case, you can, of course, do the calculation, and explicitly, too. Your monopoles are kind of, well, what is a monopole on a lattice? Well, what you want is the flux coming out of a cube to be 2 pi and to be symmetric. Now, what are your variables? Well, basically, you've got phases. If it's a U1 theory, you've got phases. And with the phases, you have they're exponentials of an angle. And if you expand for smooth fields, you can expand that, and the angles are the things that correspond to the usual gauge potentials that you have in a continuum. And the action is usually the plaquette action, which I've written here. So you take the exponential. There should be an I here, which I've missed. Sorry about that. There's an I here multiplying each one of these angles. And you've got you're summing up the angles around the plaquette. And that gives you the total value of the plaquette, and you take the real part of it, which given there's an I there, it's really the cosine of this thing. Now, so we have this kind of field theory here, the U1 field theory on the lattice. And what does a monopole look like? Well, you have a flux of 2 pi coming out of the 6 faces. So what you want is at least the action to be the same. That's what should be symmetric. But you have a constraint, which is because the angles, when you sum up all the angles around the cube, they sum up to 0, because on every plaquette where you have one angle on a link, there's another plaquette where you're going in the opposite direction, which will give you minus that angle. So when you sum up all the angles, you will get you can't have 2 pi over 6 on each face. You can have 5 of them with 2 pi over 6, and 1 of them with 2 pi over 6 minus 2 pi. Then the sum of all 6 gives you 0, as one must have. So this 2 pi here is nothing but the direct string that comes out of the monopole, and it's invisible of course, it's invisible when I take the exponential of I times the angles. This 2 pi plays no role, so the action on this particular plaquette is the same as on all the other plaquettes. And so it's symmetric in terms of its physics. But there is this invisible little direct string going out of it. So those are the, and then of course the fields go out, but the Dirac string carries on. And this is, and if you do the calculation with these monopoles, a Monte Carlo calculation, then you find indeed a nice linear rising potential. However, it's a very peculiar theory in some ways because, of course, all the dynamics is being driven by these ultraviolet monopoles. Basically, they're within cubes. They're not on physical, in any sense, on physical length scales. That is to say, their weighting is exponential of minus beta times the weighting of a monopole is something like, you know, if you look at it, it's got a certain action, which is finite. So its weighting is e to the minus, I don't know why this is playing up on me. Okay, it's e to the minus constant over g squared, because it's e to the something times beta, which is e to the something time over g squared. So in units of g squared, remember in 2 + 1 dimensions, g squared has dimensions of mass. So you might have expected that the way to take a continuum limit is to take something like the string tension, which you get from here, square root of the string tension divided by g squared and see what happens as beta goes to infinity. Well, the string tension disappears exponentially in 1 over g squared, 1 over a times g squared, because that's to say exponentially in beta, because of the fact that, basically because of the fact that dynamics is ultraviolet. So you get this rather peculiar dynamical situation. Nonetheless, it's a good model in which to see explicitly how monopoles produce confinement. But the right way to do it, of course, is with the Georgia-Glashow model, where the actual monopoles are no longer ultraviolet because their size is given by the symmetry breaking parameters in the Georgia-Glashow model. Okay. Yeah. Yeah, you can actually, that's an interesting question. In fact, well, a lot of people did, in fact, but the one thing one of the things that a long time ago I did was to ask the question, you know, you might ask yourself, there is this prescription for finding monopoles on a lattice. So, you know, how good is it really, and when is it good? Because you might think, well, if you as you lower beta, for example, and you get large fluctuations on a lattice, maybe it's just you're just picking up random things which have nothing to do with monopoles. So what we did is look at do a calculation with a Wheeler action, and that has its own monopoles because it's extra degrees of freedom on the faces which define for you monopoles in a certain way. And which is separate from the gauge degrees of freedom, although it's coupled to the gauge degrees of freedom. So that's one way of seeing the monopoles. And then you can take the same fields and use this prescription on them and see where the monopoles are. And not just comparing the average number of monopoles, but comparing the difference between the whole gas of monopoles and seeing what is the difference on individual field configurations. On individual field configurations, what's the difference between the Wheeler monopoles and the monopoles you get with this kind of prescription. And what you find is that if you take the monopoles, they are different, there are differences, but if you take the difference, what you might call the difference gas, you subtract the two gases and you get the difference between them, and then you've got a new monopole gas. And if you calculate the Wilson loops and so on with that monopole gas, you don't get confinement. And if you look at it, it seems to be mainly dipoles. So it's saying that this prescription and the Wheeler monopoles are not always exactly the same, but they tend to differ by being misplaced by one lattice on the order of a lattice spacing. So that sort of a kind of is a good you know, that tells you that this prescription as long here is actually working, seems to work reasonably well. It's a check on it. So it's so in fact, the prescription came a long time ago. I think it was originally from the paper in the early 80s by de Grand and Tom de Grand and Toussaint. They're both American, although they sound like French names, but they're de Grand. Okay, so so what we find is that in that case, in case of that 2 + 1 dimensional model, we find that we get linear confinement from monopoles, and we can ask what happens in 3+1 dimensions. Well, in 3+1 dimensions, of course, now we're really talking about monopoles which have world lines. So you have world lines, and they will have to live on closed loops of some kind. And you can ask yourself, are those closed loops large or small? If you're looking at a Wilson loop, and if your monopole loops are always small, then when they intersect the three-dimensional volume in which you have your Wilson loop, they will look like dipoles, which are close together. And their flux will cancel out. It won't actually affect the Wilson loop significantly. On the other hand, if the loops are very large, essentially like a condensate, then if they can intersect this area where you've got the Wilson loop. One of them will pass through the Wilson loop, and the other one, and the chances of the other end passing through the Wilson loop as well will be very small. It will more likely be very far away if the loops are enormously large. So really, you want to know, are the loops condensing or are they small? To know whether it's producing confinement or not in 3+1 dimensions.
Sorry, I don't know how relevant the question is, but now that you have these lines, are they time-like or space-like?
Well, it's Euclidean, so they can be in any direction. Yeah.
If I wanted to think in them, I would have.
Ah, well, that would be different. Yeah. I don't. I'd have to rethink things about monopoles, everything. Yes. Yeah. So one can discuss that, but I think that would need some rethinking. Ah, yes. Well, that's a sad thing about lattice field theory. It's originally because the lattice gauge theory in Euclidean space-time looks like a statistical mechanical system in 4 dimensions. And of course, in statistical mechanics, you've got a beta because that is inverse temperature. People decided to use beta also here. But here, it doesn't mean the inverse temperature. It means the inverse coupling. But then, of course, people still use sometimes beta for the inverse temperature. And then, of course, you've also got the beta function. So, so unfortunately, but it's really unfortunate we called it beta originally. I mean, but anyway, it's stuck. So that, no, the beta that I'm talking about here is always the inverse coupling, unless I say otherwise, unless I'm talking about finite temperature.
Yes, but for this problem, the time direction is also compactified.
It's compactified because it has to be in these numerical calculations, but in principle, it's as large as you like, very large. So we are at 0 temperature. I'm always assuming we're at 0 temperature in that phase. So, so let's think about, okay, so what is the probability of finding a loop, a monopole on a loop of length L? Suppose the action per unit length is Sm, which is something we saw before, is something with 1 over g squared, a times g squared, and so on, with some number in front of it. Suppose it's Sm, which I've written here. Oh, sorry, this is, okay, there, I've put the beta explicitly there, so that is already the 1 over g squared is there. But that, okay, so this is just some number which is summing up all the plaquettes going out of the monopole. So it doesn't involve 1 over ag squared, that's in the beta. Okay, so you've got a number here, you've got a beta here, and you've got the length of the loop. So this is the total energy of this object in this statistical mechanical system, 4-dimensional statistical mechanical system. And then you can ask, what is the entropy, which is to say, how many different ways can I have the path of length L? And that's exponential in L, with, of course, with some factors of powers of L, which I'm discarding, but not less important. But the dominant piece is an exponential in L, which is basically because if you're counting number of paths, you make one step, then after you've made one step, your path can go in a number of directions. And then after that, it can go in another number of directions. So the thing exponentiates in the total length, the number of paths. So you've got something like this, roughly speaking. And what you're asking is L arbitrarily large, or is it being kept small? And that's really a question of whether this dominates, which wants to make L small, or whether this dominates, which wants to make L large. And there's a critical point in between where they're roughly equal, which is obviously where C is equal to beta Sm, or in other words, beta is equal to C over Sm. So at this point, and this is of course not a proper calculation, but you could do much better if you wanted to. So there is a point, this is again an old argument. So there is a critical beta at which instead of having, so initially at lower beta, this is less important because this coefficient is smaller. So at small beta, this is less important than this. This dominates, and you get effectively infinitely long monopole loops in the vacuum. Whereas as you go for beta above this value, this will dominate, and now you only get small loops because of this suppression, exponential suppression here. The net suppression will be exponential once this thing is bigger than that. And indeed, as beta gets larger and larger, the loops will get smaller and smaller. So, and eventually they'll be completely suppressed. So you have a phase, so you have two phases, one where at strong coupling, where you have indeed a monopole condensate of these lines, and you would have linear confinement. And then you have a phase transition, and then in weak coupling, the monopoles loops disappear. So you don't get any confinement. And that's what we know happens when we do numerical calculations. On the weak coupling side, we just end up with free photons eventually in 4 dimensions, which is reasonable, even in this compact U1 theory. Okay, well, the next thing I want to mention, this is now a slightly different thing about confinement, is, but it is very much the reason, one of the, as has been mentioned in previous talks, dual superconductivity was a sort of motivation for people thinking about monopoles and confinement. And this, of course, well, we've heard this in detail already, but I wrote this slide before I knew we would be discussing this in earlier lectures, so I'll just quickly go through it. There's just one slide. So the thing here is, of course, that in type 2 superconductors, you know that the magnetic flux ends up being in tube-like vortices, which cost an energy per unit length. And what this means is that if you were lucky enough to find a monopole and an anti-monopole and place them in a material, superconducting material before it's superconducting, and then you lower the temperature so it becomes superconducting, then the flux between the monopole and anti-monopole would be in a tube, in a vortex, and it would cost, the cost of the energy would be proportional to the length, and therefore if you had moved the monopole and anti-monopole further apart, the energy would grow linearly, so you would have linear confinement. So that's nice, okay, as a thought experiment. So now you want to think, well, what I really want is electric charges linearly confined. So let's go to the electromagnetic dual, electric charges and magnetic charges interchanged, electric and magnetic fields interchanged. And that also means, for example, the electron Cooper pairs that drive confinement become monopole, magnetic monopole Cooper pairs. So you're changing a lot, but let's go into the details. It's a thought experiment. So in this dual system, the same thing would happen for electrons and positrons, for example. They would be linearly confined, or at least positive charges and negative charges would be linearly confined in such a dual superconductor. So that's nice. We're partway there. All we have to do now is to go from the abelian theory to a non-abelian theory. And of course, that's the sort of thing you leave as a topic for the student. There you are. Because we haven't made much progress on that. You guys have to. Yeah. Oh, yeah, so this is, yes, the one on the lattice, you mean, yeah. Offhand, I don't know, but it's worth thinking about, yeah. I don't know. Yeah, so you wouldn't have them in the same state. Yeah, you'd have to think about that. What is a, well, mind you, of course, the usual plasma we have, screened plasma, is a they're fermions, they're electrons, positrons. So I don't know. So we'd have to see. Yeah, good question. Yeah, interesting question. Thanks. Yeah, so this is the dual, my one slide on dual superconductors. We heard a much more detailed exposition yesterday from Ed there, which is much more complete. The other thing I would like to talk about, again, very briefly, and then a bit more because there are some lattice calculations I would like to show. And this has to do with actually another idea in the late 70s, I think originally, I think by Tuft, about disorder loops, loops which disorder the Wilson loops. There will be loops in 3 dimensions, and I'll stick to that for pictorial reasons, but you can do it also in 4 dimensions where there will be sort of higher dimensional objects. But in 3 dimensions, this is, so what we've got here So what we have here, so let's consider an SUN gauge field on a cubic lattice. And we want to consider a line-like fluctuation, which I'm not defining at the moment, but I will shortly, which transforms any field encircling the line by an element of the center, Z and Zn. So for example, a Wilson loop encircling this line will acquire an extra factor of Z in virtue of the fact that there is this fluctuation. So let's suppose that would be like if the Z you've chosen is -1, which is in the center, if n is even, then that would be a bit like the monopoles. It would be disordering it just in the same way, where the factors are -1. So if there is a condensate of such lines, then the number intersecting the Wilson loop will be proportional to the area of the loop, and you'll get the area law in the same way as we got for monopoles, by the same kind of simple calculations, some Poisson distribution, if you like, or some variation on it. Now, what might such a, in the modern language, we're talking here, I think, about a one-form symmetry, and this line is carrying a charge, is charged onto that symmetry. So if there is such a, it would be nice to have an explicit form, and it's easy to write down an ultraviolet version of such a line. So you take your field that you've got here, whatever it is, you've got some given gauge field on all the links of the lattice, and you transform it in the following way. Most of the links are left unchanged, but some of them are changed by a factor of the element Z that you've chosen from the center. Which let me assume it's -1 for now, just to make it easier to talk about it, but it won't matter whether I choose it to -1 or not. And what you do is you make a change on those links. Suppose what you do is you construct a line which extends in the Z direction. You've got 3 directions, X, Y, and Z here. It extends in the Z direction. You've chosen some points X and Y, which I call X0 and Y0. And you make the link going from that point in the Y direction, you multiply it by Z. And you do the same for all the links going up, which are in the Z direction. So let me go to the next slide. It's the sort of thing, the next slide I meant to do on the board, but I don't think would show up very well. So I produced a photo of a piece of paper, which also doesn't show up dramatic. But I think it's still better than doing it on the blackboard. But so here what you've got is a lattice. Not everything is shown on the lattice. Some plaquettes are shown. The single lines are the links where I haven't changed anything. This is the line I've just been talking about. So X is here, Y, Z going up. All these links here, which go into the screen, are the ones which go in the Y direction into the screen, have been given a factor Z all the way up to the boundary. And then I notice that if I do that, then of course the action has been flipped away from the action I had before on all of these, and therefore they will cost an extra action. If I don't want that to be the case, I can get rid of that by also multiplying all the links which are parallel to it off in this direction. Here, here, here. We have also made the lines thick. So the thick lines are the ones which are multiplied by an element of Z. All those have been multiplied by Z as well, going off to infinity in that direction. And all these plaquettes will have the normal values, and only these plaquettes would have a different value and therefore will cost action because of this factor of z. If I hadn't put all these into, if I hadn't multiplied these by z as well, then this plaquette would also have had a normal link here, and so it would have also acquired a factor of z, and I would have had an extra cost in action for all the guys here as well. So instead, I've pushed that off to infinity by putting in these things here. Now, of course, we're not on an infinite lattice. We are instead on a periodic lattice typically. So this, since it's periodic, at some point, this has to go back to being an unchanged link. And in that case, you find another one of these vortex lines somewhere else. So what actually on a periodic lattice, you have two vortex lines necessarily, just because it's periodic. But these are the kind of, but they could be anywhere, because these guys don't, this change in between doesn't cost any action. And actually, you can also deform these lines if you want, I mean, by doing suitable transformations. But anyway, let's stick to this. So this is a kind of ultraviolet vortex. And if, so now, if it, you can imagine that if, when this goes through a Wilson loop, which is somewhere, say here, a Wilson loop will, in this plane, in the xy plane, a Wilson loop in the xy plane will necessarily, since these lines go all the way down, up, you know, it goes right across the lattice, it will necessarily have at least one of these altered links on it, so it gets the factor of z. But when it comes back over here, it doesn't, because these links haven't been altered. So the Wilson loop gets a factor of z. In fact, any closed loop around this will get a factor of z, unless my loop is so large that it encloses the other vortex as well, in which case you lose again the this factor of z, because you've got both vortex and effectively an anti-vortex at the same time going through the Wilson loop. So this is a, now, of course, this is not a physical, it's ultraviolet. And you would actually like to see a physical example of this, one which includes quantum fluctuations, which would probably spread it out and so on. And the trouble is, in the confining phase, you can't, because it just disappears. You don't see it. However, you can see it in a slightly different context. And that is when you go to the deconfined phase. If you go to the deconfined phase, well, let me make one more comment. Not only does it disorder Wilson loops, but if you look at the Polyakov loops in the y direction here, the Polyakov loops here have their original value, while the Polyakov loops in this direction, going in the y direction, have one of these along the Polyakov loop, and so it picks up a factor of z. So all the Polyakov loops here pick up a factor of z compared to the ones here, compared to what they were before. Now, when you're in the deconfined phase, but that, of course, is not very useful in the confined phase, because the average value of the Polyakov loop is 0 in the confined phase. So whether it gets an extra factor of z or not is not something you're going to be able to see. In the deconfined phase, on the other hand, the center symmetry is spontaneously broken, and you have, if it's Zn, you have n possible vacua, which are labeled by e to the I 2 pi over n. And so, for example, in the deconfined phase, you would expect this thing to take you from something close to, say, if you're in the vacuum, if you're partly in the vacuum, if you're on the same lattice, if you have two vacua, if you have a vacuum and you have this thing going through it, it will change the Polyakov loop on one side from the other side by a factor of z. And we know that does happen in the deconfined phase. And that is an example here. So this is now in the deconfined phase on, it happens to be in SU2 in 3 dimensions. And what you see here is a plot of the value of the Polyakov loop. I've taken this from some other paper, so it doesn't have exactly my same coordinates, but never mind. And what you see here is that for Z, in this, so here, in this case, your line vortex is extended in the y direction. And it's where, on one side of the vortex, the Polyakov loops have values 1. On the other side, they have -1. They're in a different vacuum. The thing in between we normally think of as a kind of domain wall separating one vacuum from the other, the one which belongs to, say, 1 to the one belonging to -1 in case of SU2. However, one can also, since it's doing exactly the same function as one of these vortices, except it's been squashed. So, of course, by the fact that once you're above the deconfining temperature, the extent in time of your lattice out of these 3 dimensions, it's one of the 3 dimensions, is now much smaller, and it's sort of squashed down the your vortex. It's and when you squash it down, it acts as if this vortex is now in a kind of Higgs phase for the vortices. It becomes a real object you can see. So I just wanted to mention that because I think it's quite interesting. If you want to see a real vortex, one of these vortex lines which carry the symmetry, you can, I believe that the domain walls you see are probably, that's what they are. That doesn't tell you, of course, whether those whether those objects actually do play a dynamical role in the confined phase. Unfortunately, it doesn't tell you that, but it's kind of interesting that you can examine them a bit in this particular phase, the deconfined phase. Okay, so that's one of the points I wish to make. That was actually this was actually taken from a single field configuration, but at a very high temperature, 30 times the deconfining temperature. So the fields don't fluctuate very much. That's why this looks nice and smooth, although it's one field configuration. It's not an average over many. If you go, to a lower temperature, still in the deconfined phase, just twice the deconfining temperature, then things are much more jagged, and because the polyacrylic fluid does get normalized by quantum fluctuations. But still, the domain wall is there. Now, you might ask, how come I can see just one domain wall on a periodic lattice? What happened, because this is supposed to be periodic? Well, the way that you do it is that you can actually use twisted boundary conditions so that you can effectively enforce a single. If people want to know, they can ask me the tutorial this later today, how you do that. Okay. So let's see. So now let's move to a couple of SUN. The argument I gave for the fact, this phase transition for monopole lines in 3+1 dimensions in the U1 theory, the fact that you've got a phase transition with confinement one side, deconfinement on the other, because of this simple kind of counting argument between the entropy of lines and so on. You can do that the same for the confining flux tube. And again, this is an old argument I thought I would mention in case you haven't met it. So suppose you have you're in low temperature, you're in the confining phase, and you've got a confining flux tube between 2 fundamental sources, some distance L apart. Their sort of weight in the partition function would be an exponential of minus the energy sigma string tension times L, of the energy of that flux tube divided by the temperature. That's the suppression factor, so Boltzmann factor. But then, of course, you've got the number of ways you can have a flux tube of length L, and that's again an exponential of some constant times L. Constant is not the same as the one before, but it's some constant. And of course, other factors that I've neglected, power factors. And then again, for the same reasoning, there will be a phase transition from this at sigma over C. For higher temperatures, for high temperatures, for low temperatures, this wait a second. For low temperatures, it should be well defined, and for something wrong with the way I wrote this, I think. Anyway, the conclusion should be that it's well defined for low temperatures, your linear confinement, and flux tubes condense. Yeah, that's right. Of course. For large times. For large temperatures, this factor is suppressed, and you get, and this dominates, which means that you get infinitely long flux tubes. The flux tubes condense in the vacuum. And if the flux tubes condense in the vacuum, it means it costs you no energy to pull apart the sources. There's just the flux tubes everywhere there anyway for free. Whereas if you're at low temperatures, there's a more rigid kind of flux tube, and it's costing you energy, and you don't get long flux tubes. It'll be close to the minimum distance between the sources by this argument. So in between, there should be a phase transition. Now, of course, in practice, earlier in these lectures, I talked about the phase transition in terms of a plasma and confined states. And in practice, I think that is the one that in all the SUN cases is the one that happens at a temperature which is lower than the temperature at which this would happen. And therefore, it's the one that gives you the deconfining transition. It's not this factor. But even if that did not happen, if you didn't have that dynamics, you would still get deconfinement on these by this general argument, just looking at strings and the entropy and the energy entropy balance. So that's okay. So let me just say a few words about what one has seen. So some of the things was just ideas I was talking about. And then I would also like to say something about some of the facts, it's not just some of the things we've learned on the lattice, which are kind of facts, you know, just in case that's useful for you in thinking about confinement, different aspects of confinement. So one of the things we've learned is that in 3+1 dimensions, we do have a deconfining temperature, which if we express it in terms of the square root of the string tension, we can calculate its continuum limit. And having calculated the continuum limit, we can do a plot of this kind for the different SUN groups going from SU2 up to SU12. As you can see, they all fall nicely on a plot where the leading correction is 1/n². That's almost better than it should be, because after all, SU2 is second order, SU3 is weakly first order. These are reasonably strongly first order. So you would have thought that, you know, there could be some sign of these being slightly different, the dynamics being slightly different and whatever. But oddly enough, it falls perfectly well on a straight line fit like that. Just the leading order 1/n² correction is needed. And it may be interesting to look now at what people believe they know about the phase diagram of QCD, of deconfining temperature. So this is one of the plots that appear in reviews. It's called a Columbia plot, because this way of plotting it was originally came from Columbia, well, I think Norman Christ's group. And so what have you got here? So this is now QCD with 3 fermions. So here what we've plotted is where the words tell you about the deconfining transition. And the axes are, first of all, here you've got the 2 light quarks, the up and down quarks. So there are 2 quarks which are taken to be degenerate here, and 1 strange quark which vary independently. So here are and you're looking at how things depend on their masses. So the physical point labeled here is this is supposed to be the physical quark masses, and this is where we are in real QCD. But people have, of course, been able to explore. That's one of the nice things about doing lattice calculations, is you can explore, you can go away from the physics to get some insight maybe by putting it into a wider context. You also see, before I go into talking about this a bit, you also see some question marks. I didn't put them there. They were there originally in a review, which was, I'm not sure if it was in this review or a few years before that, but one of the authors was the same. In a later review, the same plot arises, but without the question marks. But I don't believe that's because these, whatever the issues were, they've been resolved. I think it's just to make a neater plot. I suspect that there's quite a lot here that we don't know, because we haven't actually numerically studied all, you know, with any kind of fine grid, all these masses. What I think we do know very well is that if you have infinite quark masses, you are in the pure gauge theory, and it's first order. The phase transition is first order. As you move away from there, it remains first order until the masses drop below a certain value. And then on the edge of this region of masses, it's there's a second order phase transition. After that, you have a kind of crossover. You don't have an exact phase transition. Now, you expect heavy quarks to make not too much difference, because if you think, so you've got these heavy quarks, what do? There are loops in the vacuum. And which loops are important? Well, if you think about the Zn symmetry that I discussed earlier, formally the Zn symmetry is broken by the action, the fermionic action, which is just field, link variables, fields. It's broken by that, so you no longer have the center symmetry if you have fermions. However, in which situation is it really broken? If you think about usual discussion with the center symmetry, how you use it, you actually transform a set of links in one plane on the lattice, in one slice, time slice, say, on the lattice, one set of links pointing in that direction, and you transform them by an element of the center, and then you discuss whether what is affected by that and what isn't affected by that. Well, if you have heavy quarks, the only loops that you get in the vacuum from the quarks are small loops, because large loops, large propagators, will be suppressed because of the large mass of the quark. In particular, any winding loop by the quark would be suppressed. So there are so effectively, for very sufficiently large quark masses, you would have no quarks winding around the torus, and therefore they wouldn't be breaking the symmetry, the Zn symmetry in practice. There will be an exponentially small breaking. So it's not surprising that you maintain the first order transition for quite a while as you decrease the quark masses. And then at some point, you start feeling the breaking of the symmetry, center symmetry, and you get a crossover. So this is one of the things that's happening here. The other thing that's happening here is that as you move down here, there's actually quite a big change in the actual deconfining temperature. Up here, if you put it into physical units in the best way you can, you get something that is roughly 300 MeV for the deconfining temperature. By the time you get to the physical point and look at the crossover there, it's around 150 MeV. And what's happening also is, if you look at this, at the variables that define this transition, it looks more and more down here as if what's happening is that you're talking about chiral symmetry breaking and chiral symmetry restoration across the phase transition. At high temperatures, you have chiral symmetry, spontaneous chiral symmetry breaking, and at low temperatures, you have chiral symmetry being broken. So there are things we don't know, but that's the sort of thing you have. And then and people have explored just a bit have explored smaller masses, and the indications are that you go back to being a first order transition once all your 3 quark masses become very small and head towards 0. And of course, there is another region, which is when I talked of chiral symmetry, there's another region which is quite interesting, and that is the one where the up and down quark masses are both infinite. In that case, you only have 1 quark left, the strange quark, in the system. So you're talking about the chiral symmetry becomes a U1, and there you have the axial anomaly. So you don't actually have Goldstone bosons when you're down here, and you don't really have I guess, a chiral symmetry to be spontaneously broken in the usual sense. But that hasn't. Some people have looked at NF equals 1, but I don't recall whether they've addressed these questions or not. So this is what you find in full QCD. And this is all confining. However, of course, you wouldn't want to be using our usual criteria like Wilson loop, area law, and so on, because flux tubes are broken by quarks and antiquarks. And the discussion of confinement, once that happens, becomes needs a more sophisticated discussion, which I'm not sure if a really good discussion of that kind is equivalent order parameters, something equivalent to the Wilson loop, is really, people have got suggestions, but I'm not sure if there's anything that we all agree on. Okay, which is all very odd, because QCD is, of course, why we believe in confinement, after all. I mean, that's the confining theory, and all the rest of the stuff we look at, pure gauge theories or whatever, is a offshoot of that, if you like, looking at confinement in those theories. And yet we don't have such a decent criteria, neat criteria for mathematical criteria for confinement in a theory like QCD.
Here, when you say first or second order, I guess what it means is that at the critical temperature, there's some quantity like the speed of sound, something that jumps. Is that like?
Well, the first order, that's right. Various things jump. Everything jumps, you know, at the first order transition. There is a discontinuity. At the second order transition, you would have a diverging correlation length of some kind. It will be a continuous transition. So, and then with the crossovers, they they look like a transition, but it's not a singularity in the partition function, as far as you can know, or derivative or anything. Well, that would be nice to know. I mean, the thing is, people, you know, we've done pure gauge at various colors, so I know what happens with the deconfining transition in the pure gauge theory. However, people haven't done these kind of calculations, which after all are these extremely expensive calculations in SU3. They haven't done them for, it would be very good to see them in SU4, SU5, SU6. For one reason, all these resonances which decay in SU3 would become narrower and narrower, much better defined. Some things would disappear. For instance, some of these states just under 1 GeV in the real world, which some people think are molecular, those would presumably disappear if you go to larger n, because that's there will be color singlet states which are interacting with each other, these two things, so, and producing a kind of molecule. So that if they are molecular, then there would be disappear. So there's all so there's a lot of interesting things, including, you know, what happens to the finite temperature and so on, if one did that. So one has to convince people like you know, like Fodor, that he should be doing SU4, SU6, SU8. Not much more necessarily, but that would already tell her. It'd be very interesting. Yeah. Okay. Well, these were just comments that I actually made already. So here are some other theories people have been looking at. So SUN is, of course, the one that we've focused upon. But in looking at the confinement transitions, people have been interested also because it tells you something about confinement at other Lie groups. For instance, the symplectic one, the SP groups. The SP group, every time I press it, it jumps by several. Oh yeah, okay. So SP group, this symplectic group, there what you find, that has got a Z2 center for all SP2n, however large n is the center is Z2. It's the same, but you find that while SP2, which is exactly identical to SU2, is second order, just like SU2, that phase transition, SP4 and SP6 are first order, and despite the fact they have the same center. So the reason people did this calculation was to see whether it was the center that played a role in whether you had second order or higher order or first order transitions, or whether it would be more likely to be the size of the group, the number of gluons you have. And so the conclusion was really it looks as if the center itself doesn't affect the order of the transition. It is really the size of the group that matters, which sort of makes sense, the number of gluons you have in the confined phase. So that's a nice calculation. Another one, here you can see linear confinement in SP2N theories. Another interesting calculation is G2. So this is no longer one of the ones with the, this is one of the exceptional groups. And its interest is that it has no center, but in addition, it's the adjoint fields are 14 dimensional, and those are the gluons. So you have these gluons in the theory, this 14 dimensional representation. The fundamental is a 7 dimensional. However, and this doesn't, it's very counterintuitive because this doesn't happen in SUN. If you take 3 14s, you get a 7 and a lot of other stuff, but you get a 7. So you can actually, you get a fundamental out of multiplying. So 3 gluons give you a fundamental charge along with a lot of other stuff. So you can actually break a fundamental flux tube in G2 with gluons, pure gluons. And you know, the comment is that's a bit, therefore the physics might be a bit like QCD. Maybe you can see string breaking and so on. So, and it has no center. Now, this theory has a first order. The people who did this calculation, they find that the deconfining transition is first order. And you also find confining strings. Here is a simple plot. How convincing it is, well, you know, this is a tough calculation and doesn't go out an enormously large distance. But here it looks linear. It's at least is looking linear up here. So this is the fundamental. And in addition, they took sources in different representations in this calculation. The 14, which is the adjoint, and 27 and 64. And if you scale them by quadratic Casimirs, the potential, they all lie on top of each other, which is kind of, you know, so it suggests that everything is proportional to the quadratic Casimir here. But the accuracy of these calculations is obviously not so great that you wouldn't see, you know, small deviations from these falling on top of each other. But it's kind of interesting that this is what they find. It should, that's the point, because they can break the string. And in a moment, I'll show you they did both. This is in 4 dimensions, but they also looked in 3 dimensions where they could do things with greater accuracy. And there you have a plot where it's linear, and then at larger distances, it breaks off. So I'll show you that in a moment. Presumably here, you could see the same thing if you had the sufficient accuracy to go further in the separation out here somewhere to break off. Yeah.
What sets the scale? Because here you have the scale of confinement, which is given by the slope, but then you will have another scale that is which it flattens.
Well, because presumably, well, let me, when I get to 3 dimensions, I should say that, because they will see it flattening. So, okay, I'll switch now to 2+1. I just mentioned there's some interesting things there. People have also looked at SP2 in there. They've looked at G2, SUN, obviously, and also SON. So I'll try to say something about these. So here is G2. I think that's quite interesting. So this is several calculations at different values of the coupling. That is to say, different lattice spacings, where you've normalized this. So this is a fundamental potential in 2+1 dimensions with G2. And what you've done is you've scaled everything by the square root of the string tension, and the string tension you got from this linear piece here. So you first fit this. Originally, it's in lattice units. You fit this, and that gives you A times the square root of the string tension as some number, which you then use to rescale your potential and your distance with in order to express things in this physical units of mu. Mu equals square root of the string tension of that representation. So that looks quite nice. Now, it goes up to a distance of 3. And then they also show something which goes beyond the distance of 3. And here it flattens off. And these are the masses, estimates of the masses in these same units of the states that it turns into. Now, okay, well, they're called glue lumps. So one of the things that, if one wants to see this kind of string breaking, very often, I don't know whether they did that or not. I looked at the paper, but I wasn't sure. Normally, you have some operators which are designed to calculate the potential, and if you just use sort of Wilson loop type of operators for that, you would probably have not seen this breaking. At least in QCD, it's hard to see the breaking if you do that, because you don't have a very big overlap onto the broken states. And if you don't have an overlap, if you don't have a sufficiently big overlap of your operator onto the broken state, it behaves essentially like looking at a very narrow resonance with errors. You don't see that it's got a finite width. So you think it's maybe stable. So the same thing can happen with a flux tube. But what you can do is you can put in operators in addition that consist of 2 of these, the broken state. If you have that in your basis as well, then you can see the broken states. You can see this breaking very well. But I suspect that there is an excited state which continues linearly upwards here, and here as well, which is a kind of a slightly unstable flux tube. But I'm not sure about that. But I think that's what would happen in QCD. Anyway, you can see the breaking, which is nice. Okay, oh well, so we now switch, that was G2, now we go to 2 + 1 SU6. So here is, we're in 2 + 1 dimensions, back to our SUN theories. We look at SU6, which is of course larger n. And before I showed you plots like of the ground state. So here is the ground state of, this is a flux tube winding around a torus now. So we're back to that kind of state, a flux tube winding around a torus of length L. In physical units, I've expressed it in here in terms of the string tension itself and the energy in terms of the string tension. Again, by getting the string tension in lattice units. These originally are in lattice units, and then I get rid of the lattice spacing because I've got the string tension in lattice units. So we've got this here. We're plotting the energy against the length of this flux tube, which winds around the lattice. And we've got the ground state, which is nice and linear, but we also have some excited states. Here there are 4 states, 2 with positive parity, 2 with negative parity. This one has a positive parity. And then there's a whole cluster of states here where we've only shown the lowest 2 because otherwise it would be quite a mess. But what you see, and the lines that you see are given by this formula, which is the extension of what I said was the light cone quantization formula for string. But extended to excited states. There is the same, you can derive the thing for excited states. So this is just the if you like, the Goldstone modes of the transverse fluctuations, the massless transverse fluctuations of the string that have been put into this in a particular way, as string theory tells you should be put in. And so you see it goes, it's even for the excited state, it works pretty well. Then at some point around here, you start deviating. This is a quite short length, remember, because the flux tube itself probably has a width which is of order of the square root of the string tension. And in fact, the length at which you can't do this anymore is given by this purple line, because at that point, the length becomes equal to the inverse of the deconfining temperature. And beyond that, although I've called this a spatial direction, beyond that, you've lost confinement. So you're in a different phase. So, but you can go very close to that and still have things following this formula quite well. So that was always quite impressive, even for that these excitations of these thick flux tubes really follow this very simple formula all the way down here. And there'll be much more about this from Sergey next week, about these kind of understanding these spectra. Okay, I won't say anything about that. Won't say anything about that. SO2n, well, SO2n, a couple of comments about SO2n before I finish, and SO2n plus 1. SO2n, and this is in 2 + 1 dimensions. The reason we haven't done that in 3 + 1 dimensions is because it so happens that with the plaquette action, this transition from strong to weak coupling that I mentioned, sort of first order transition that you see very often first order, sometimes weaker than first order, transition from strong coupling to the weak coupling, which in SUN occurs at quite a big lattice spacing at quite small beta. So you don't mind, you can do calculations beyond that. In SON, in 3 + 1 dimension, it happens to occur at quite a large beta. So if you wanted to start doing weak coupling calculations, you have to go beyond that. The lattice spacing is pretty small there, and you would need enormous lattices. So we didn't do that. At one point, we'll think of a more intelligent way of approaching that problem with some improved action or whatever. But anyway, in 2 + 1 dimensions, you can do these calculations. And remember, 2 + 1 dimensions, I didn't emphasize this, but 2 + 1 dimensions is in some ways similar to 3 + 1 dimensions. That is to say, the coupling G² has dimensions of mass, which of course is not similar to 3 + 1 dimensions. However, what it means is that the dimensionless coupling constant, when you're looking at physics on some length scale L, is actually g squared times L. That's your dimensionless coupling constant expansion parameter that effectively you will get when you expand in perturbation theory on a physics on scale L. And so as you look at things at short distances, g squared L goes to 0 linearly in the distance. So it goes to 0 much faster than asymptotic freedom. It's a super renormalizable theory. And at the same time, it blows up pretty fast also. Probably not faster. The logarithm has a funny blow up at a large scale. But never mind, it also goes, you also have infrared slavery in the sense that the coupling gets large as you go to larger distances. So in that sense, and also it has linear confinement and these phenomena. So of course, some things are different. The rotation group is different, it's abelian and so on, you're in a plane. But in many ways, it's quite, it's a good laboratory in which to do things. Okay, there's 1 or 2 points. One thing I would like to mention is that this is one situation in which you realize you have to be careful. All the calculations I did before, I was talking about our gauge invariant operators being traces of closed loops. In SO2n, there is another operator that's gauge invariant, which is based on the Pfaffian operator, which, so an operator like this in SO2n, where these themselves are closed loops, here they're the same closed loop, but they could be the different closed loops which end up at the same point. That is gauge invariant. And so it's another possible operator. And originally, I should say, you know, I was fooled by the situation. I didn't think of that. And when I did these calculations, I realized there was a problem because, you know, some of these SON theories are have the same Lie algebra as SU4. So for instance, SO6 is like SU4, has the same Lie algebra. So you would expect quite possibly the glue ball spectra to be identical. And indeed, if you look at the positive charge conjugation states, they are identical within errors. However, the negative charge conjugation states have no, the SO6 is real, you don't have them there. The trace is always real. But that's a puzzle because, you know, the excited states, C plus states that you have, some of them will decay. Most of them will decay once they're very heavy, and they will decay in SU4. They will decay, amongst other things, into C equals minus states. That will contribute to their decay width. So if those, if the SO6 is supposed to be identical to SU4 for the positive charge conjugation states, where are those C equals minus states that it should be decaying into? And in fact, it turns out the Pfaffian is orthogonal to the trace, and it gives you the states that you get from that are precisely the C equals minus states in SO6. Now, if you go, you can see that the number of operators you have here in SO2k is k. So as you increase the size of the group, you increase the number of operators, fields you have here. So it's a bit like the baryon. You would expect the masses to grow with the order of the group. And so then they rapidly become irrelevant, presumably. So that's one little comment. Okay, so last comment then, getting to the last comment. SO2n, looking at now at confinement properties, SO2n has a center which is Z2, while SO2n plus 1 has a trivial center. And so flux tubes can break. There's no center symmetry argument to prevent flux tube from breaking in SO2n plus 1. And in particular, if you take, for example, SO3, that has the same Lie algebra as SU2. And in fact, the fundamental of SO3 is really just the adjoint of SU2. And in SU2, you expect the adjoint to break because it's broken by the gluons. And indeed, in SO3, the gluons also belong to the adjoint, so they can break this fundamental flux tube in SO3. So does that happen? Well, it happens in a kind of interesting way, which again is slightly puzzling. So, well, first of all, I say that you know, in SO3, you find that the ground state looks as if it's nicely linear in distance. You have linear confinement. And then if you look at the excited states, you see something more interesting. So here is a correlation. Here is actually a correlation function from a particular lattice at some particular coupling in SO3. And I've looked at not just the ground state, but the excited states as well. So if you look at the ground state here, that's this, the points here, they show no sign of being broken. It just goes down, a simple exponential is the lighter state. That's the same for the next state, the next state, and the next state. And then when you get to what you think is the 8th excited state, you suddenly see that it breaks off. And here you have a vacuum expectation value developing. And for the 10th state. So it's quite bizarre that when you do this calculation SO3, you expect the flux tube to break in some sense because you don't have the symmetry. But what happens is that the ground state shows no sign of breaking, but instead it's the what you think are very highly excited states because they originally start, their correlation functions initially drop very rapidly, but then they flatten out because they project onto the vacuum. So that's kind of bizarre. Whether that's telling you something interesting, I don't know. Another bizarre thing, which is amusing, is, let me look at, what is this? What is this? Never mind. Ah, yes. Yeah, here. So if you look at SO2 and SO2n plus 1 and look at the deconfining temperature, they all lie on the same curve. There's no difference, despite the fact that they have different, this has a Z2 symmetry and this one doesn't. So here they are going off to n equals infinity. And they go to the same value as they should because the planar diagrams are the same as SUN. And one sees that that is actually the case, except the corrections are 1 over n in this theory rather than 1 over n squared. So you plot against 1 over n, the leading correction. But what's also interesting is that because I mentioned that the strong coupling region extends to quite large beta, so you can calculate the deconfining transition also in strong coupling. And if you do that, and you know, what you find is you find these 3 points in strong coupling and these points in weak coupling. And these points lie on, and this is now just in SO4. So I'm looking in SO4 and I'm plotting this, taking the continuum limit. So strictly speaking, I just take these points. This is the continuum limit because these are in the region which is in weak coupling. However, if I look at the strong points calculated in strong coupling, they also lie on a linear A squared. That leading correction also works for them and seems to go to, you know, almost as if you could do a continuum limit for the strong coupling calculation, strong coupling phase. Now, it may be that that is just an accident, but it may be that what's happening here is because the strong coupling region for some reason extends to such large beta, your effective action decomposition of the plaquette action, which is in powers of A squared, may be a good decomposition, whereas perturbation theory is still very poor. Maybe that's what's happening. I don't know, but that's or it's an accident. But it's or it's an accident. Sometimes, so I had several things here which were peculiarities that I thought I would show to you, just so that because these are also things one finds on the lattice. Sometimes, as I remarked today, someone else, sometimes when one goes through this kind of thing, one feels like one of these 18th century explorers who come from the distant parts of the world with very strange objects back to England, and they show them to everybody. Everyone's excited. No one's ever seen this before. And they come back also with tales that other people have told them of dramatic things, which turn out in the end not to be true. But so sometimes the danger is you end up acting like that when you bring a whole group of things which are peculiar. But they are. But I think that some of these may not be significant, and some of these may be significant. So in any case, I'll stop this set of lectures here, and in the tutorial, if you have questions, there's a good opportunity to ask. Thank you.
Thank you for a wonderful talk. And I think we have room for one, and then we can go to coffee. Let's thank Mike again.